So hello and good afternoon, everyone. Thank you for joining us for our virtual speaker series and today's topic, Colorado's Desperate Drought Outlook. My name is Holly Riebel. I'm the Executive Director of the Headwaters Center. Also with us today is Evie Guay. She's our manager of Headwaters River Journey Water Conservation Museum. The center's mission is to bring awareness and educate the public on the importance of healthy rivers and its impact on our everyday water use, the environment, education, recreation, and our economy. If you haven't visited this center, I encourage you to bring your family for a fun, interactive experience or register for one of our events and educational programs that can be found on our website at headwatersriverjourney.com. We are excited for today's speaker, which is Peter Goble. Peter is a service climatologist and drought specialist for the Colorado Climate Center at Colorado State University. Peter received his master's degree in atmospheric science in 2016 and was hired on as a researcher. His time is split between research and education outreach. His research focuses on the role of soil moisture in seasonal weather and water monitoring and prediction. Peter is an avid runner and skier who enjoys Colorado for the plentiful outdoor recreational options. He lives in Berthoud, Colorado with his wife, Jessica, dog Midnight, and two cats, Eleanor and Orion. So welcome, Peter. Before we begin, I've just got a few housekeeping rules. We will be recording this, so I'll have everyone's mics, and if you could turn your pictures off as well. Your videos. If you have any questions, please raise your hand or ask it in the chat room. There will also be time at the end of the presentation for any questions. And with that, let's get started. And Peter, I'll turn it over to you.
All right. Yeah, thanks, Holly. Thanks for having me today. Looks like we've got kind of a small crowd, so feel free to interrupt me or throw things in the chat. I've got a chat window up so we can talk about things at any time. Like Holly said, I'm Peter Goble, and I work with the Colorado Climate Center. All right, so just a little bit of what to expect throughout the next 45 minutes to hour. I'm gonna give a brief introduction of what the Colorado Climate Center is, who we are, what we do, and how you might be able to use us as a resource. Then I'll talk some about the history of weather observations in Colorado and what we've learned throughout our time taking weather observations in Colorado. So we'll talk a fair bit about what our climate looks like to set the context for the later parts. I'll talk about how our climate is changing and what we expect going forward. And then I'll look at a shorter time scale, just what to expect might be coming down the pipeline over the next couple months or so. And then I'll go ahead and tell you a little bit about how you might be able to help us do a better job monitoring the climate of Colorado. So the Colorado Climate Center is a state climate office, and the concept of a state climate office goes back to before 1973, when there was a program, a federally run program where each state had an appointed state climatologist who was expected to use their expertise to serve the public in climate-related matters. But it was abolished in 1973, and since then it was really land-grant universities that picked up the slack and decided this was a really valuable service. And so the Colorado Climate Center is largely supported by the Colorado Agricultural Experiment Station. And so when you think Colorado Climate Center, definitely think agriculture focused. We do a lot of work with agriculture, but we talk a lot with about water and water availability. I'll definitely be talking about that today. So we have a 3-pillar mission, and this is a photo of our team on the right-hand side there. But our mission, again, is it's climate monitoring. So that's data collection. Those of you on the call, you may have heard of the Community Collaborative Rain, Hail, and Snow Network, or COCORAS. It's a nationwide precipitation monitoring volunteer program. The Colorado Climate Center runs that. We also run the Colorado Agricultural Meteorological Network, or COAGMET, which is a network of about 90 agriculture-specific weather stations around the state. We do a fair bit of climate research as well, making sense of the data that we see, and then climate services, which is stuff like this, just sharing what we've learned with the public. All right, so now I'm going to get a little bit into the history of weather observations in Colorado. And certainly people have been monitoring the weather in Colorado for much longer than 130 years, certainly for centuries, but our modern weather observations taken with instruments go back to the mid to late 1800s. And here we're looking at a map of weather stations across the state in the year 1890. And these weather stations were primarily to measure temperature and precipitation. And at the time, they were actually run by the US Army. You can see a couple stations here in your area, Fraser and Grand Lake. We still use that Grand Lake station a lot today because it's still putting out a lot of good data. These weather stations were later taken over by the National Oceanic and Atmospheric Administration, or NOAA, and formed the Cooperative Observer Network, or COOP, which is really our foundation or backbone for our understanding of climate across Colorado and the state today. One of the things that's, of course, very important when we look at climate in Colorado is our water. And as you well know, being in the Headwaters region, we are a Headwaters state. We don't get water from any other state. We just get what falls here due to our high elevation and intercontinental positioning. So throughout the cold season, it stays cold enough that snow can accumulate more quickly than it melts in the high elevation. And that seasonal snowpack, when it melts in the spring and early summer, it gives us most of our water for the year. So in order to get ahead of our water supply needs, we closely monitor snowpack in our state. And this is an example of a couple researchers doing that a long time ago. I think this photo is actually from the 1930s, where they're doing what's called a snow survey. You can see they've got that long metal rod that you actually drive into the snow and then weigh the contents that you're able to core out. And that tells you about your snow water equivalent, or how much water is in the snow. We think of that as snowpack. So those are pretty fundamental to our understanding of weather and climate in Colorado, as well as just a key variable that we need to sample year after year. Like I mentioned, we run the COAGMET network, or the Colorado Agricultural Meteorological Network. Here I'm showing a map of all the weather stations in the network, as well as an image of our station in Westcliff. And what makes these stations special is they really have an agricultural focus, but also a water usage focus, because they're designed not just to measure temperature and precipitation, but also cloud cover, surface humidity, and wind speeds. And when you put all those together, you can make some really solid estimates about how much water a given crop will use throughout the growing season. And so these weather observations are crucial, especially considering that most of what's called our consumptive use of water in Colorado, or the water that we use that doesn't just get treated and put back into the water supply, is used in the agricultural sector. So we've got all these weather stations across the state that we can learn a lot from, but when you look at weather data, you're often looking at maps or gridded data, and these data are often spatially complete, or they show you data for everywhere. How can you do that when you only have these pinpoint weather stations that tell you about one location? Well, that's where things like satellite observations come in that can help us fill the gaps in our knowledge in weather. And the surface weather stations are still very useful because they're needed in order to calibrate tools like this, as well as serving other purposes. So you put all that information together, and what do you get? Well, first I'm starting with just a digital elevation map of Colorado, where you can see in red the Eastern Plains, and then your area of the high mountains and Colorado Rockies in the purples and blues and greens, and then the rugged western slopes with your mesas and hogbacks and ravines on the left side of the image. And the reason that I'm showing a digital elevation map is when we look at our climate maps, you're going to see that elevation is a crucial driver of climate across the state of Colorado. So now I'm going to show some precipitation and temperature maps. And this one is showing annual average precipitation in Colorado. And if I toggle back and forth between the last map and the current map, you can certainly notice some similarities. The higher elevation areas are wetter, the lower elevation areas are drier. And so the reason for this is fundamentally when weather systems track across our state, the air either has to go around or over the mountains. When it goes over the mountains, that air must rise. As the air rises, it cools. And as it cools, the water vapor in the air is condensed out as rain, or as is often the case, as snow. You'll also notice that in general, the westernmost mountains are wetter than the easternmost mountains. Certainly, if we compare areas like the Elk Mountain Range to just downstream towards, say, Pikes Peak, much wetter in the Elk Range. And this is largely because as weather tracks across the state, it usually comes from the west or northwest. And so as it flows across the state, it's going to hit those western peaks first. And so that's when there will be the most water vapor still available. And then when it hits other mountain ranges, it's kind of like wringing out a sponge multiple times. All right, this is a bit of a tangent, admittedly, but also just a fun fact about Colorado. Each month is the wettest month of the year somewhere in the state climatologically, and we're the only state in the union that can say that. Perhaps more importantly, for the northern half of the state, we tend to be wettest in spring, April, May, and the southern half tends to go more July and August. There's certainly some nuances to that we can discuss. But as far as why the northern half is wettest in spring, there's an old saying that as the days get longer, the storms get stronger. There's some truth to that. Spring is when you see the biggest temperature differences between the southern US and the northern US, or up on the Canadian Shield, where it's still very cold in April and May in those areas, but gets quite warm in the southern US. And those temperature differences lead to air masses of different density. And when you have air masses of different density collide, you get storms. And when those storms track across Colorado, they give us plenty of rain and sometimes snow. Now, as we look at southern Colorado, you'll note that oftentimes it's the summer that's the warmest. Perhaps the biggest reason for this is that warmer air can hold more water vapor. So when it does rain, it pours, you get more rain in a short amount of time in the summer. But then also it's thunderstorm season, and you're well acquainted with this in the Headwaters area as the mountain peaks heat up under the hot summer sun. That air gets warmer than its surroundings, less dense, and again we have differences in density in air, and so the less dense air rises, and as it rises, that creates our thunderheads. And on a good day where those thunderheads are particularly vigorous and have the energy to be pushed out onto the plains, they come out in lines of sometimes severe weather across much of the eastern plains. So we talked a little bit about what the wet season is, but what do you actually get? Well, it turns out that the weather is quite variable based on what pressure patterns the atmosphere puts us through, whether we're stuck under high pressure for an extended amount of time, or whether we get some really good storms. And so what I'm showing here is monthly temperature observations with the month on the x-axis and the precipitation amount on the y-axis for the Grand Lake weather station from 1940 through 2021. And you can see in any given month, we can be all over the map. So it's highly variable based on what the wind blows in. And in terms of how things may be changing over time, this is a time series of average precipitation throughout the state. So, in the Headwaters region, you get more than 18 inches generally in most places, especially up on the mountain peaks, but the average statewide is only about 18 inches. And we don't see a real clear trend over time, but we do see that recent droughts have been fairly brutal, like 2002, 2012, and 2020. 2018 was a pretty bad one as well. You may have heard the most recent 21 or 22-year period referred to as a single drought. And I take a little bit of umbrage with that classification because we have had some wetter periods interwoven within that time frame. It's just that our dry years have been really bad. And, you know, it would be one thing if the wet years hadn't recharged our water supplies, but in years like 2015 or 2019, our water supplies have actually done quite well. It's just that we only store enough water for in most parts of the state a year or two, if maybe 2 or 3 if you're lucky. So drought comes back quickly if the precipitation doesn't fall. All right, now we're going to look a little bit at some temperature maps, and here we're looking at, on the left-hand side, average minimum temperatures in January throughout the contiguous US, and then on the right-hand side, average maximum temperatures in July. And one thing that you'll notice right off the bat is the mountains stand out as cold in any season. And I remember being on a hike once with my brother and my dad when we were just kids, and my brother asked, you know, why aren't the mountains warmer? You're a mile closer to the sun. Well, it's a good question for a kid to ask, but then it turns out if you're 93 million miles away from the sun, being a mile closer doesn't make a whole heck of, well, it doesn't make any difference really. But the atmosphere is only a few miles thick, and the atmosphere has greenhouse gases that help to insulate us. So you're less insulated higher up in elevation. So it's kind of like having a thinner and thinner blanket. And we'll talk more about greenhouse gases here in just a little bit. Uh-oh, what's going on here? Hang on, I'm going to stop my share and figure out, just troubleshoot this real quick. My apologies.
Okay.
Okay. Can you see my screen again?
Yes.
Okay, perfect. Sorry about the hiccup there. Yeah, we were just talking about the high elevations are much cooler than the low elevations, and it turns out this effect is quite large. So if you look at the average annual temperature of the top of Pikes Peak versus Los Animas, which is in the Arkansas River Valley about 100 miles away, it is as big a temperature difference as the annual average temperature difference between Florida and Iceland. So while we do see that things like latitude make a difference, with the northern half of the state being warmer than the southern half, elevation absolutely trumps latitude when it comes to climate in Colorado. If you are familiar with plant hardiness zones at all, this is a map of plant hardiness zones across Colorado. And plant hardiness zones are just designed to show how cold do we expect the coldest of the cold air in winter to be. And this is an interesting case that I like to show because it's actually not the 14ers where we see the coldest of the cold temperatures occur in Colorado. It's the high mountain valleys like North Park, like South Park, like Alamosa in the San Luis Valley. And the reason for this is on calm, cold winter nights when the air is still and cold, that cold air gets dense, and the dense air sinks, and the dense air pools in the high mountain valleys. So you end up with really cold temperatures in the valleys on winter nights. You might be looking at areas like Grand Junction and Palisade and think, well, why do they stay warm? They're also in the low elevations. And it's because that air doesn't pool in Grand Junction and Palisade. It continues to drain down the river valley. And as long as that air is moving and mixing, it doesn't get quite as cold. And then kind of like I showed with that plot with precipitation, this is a plot of what you actually see in terms of temperature. This is, again, looking at that Grand Lake station throughout the course of a year. The brown range shows the average maximum and minimum temperature range throughout the year. The blue line shows the record min for each day, and the red shows the record max for each day. The blue bars show what we actually observed in 2021. You can see a spell of record wet weather there in the middle of June. And then similar to precipitation, again, here is a plot of statewide annual average temperatures. And we can see that there is a trend here. Things have been warming considerably since the 70s or 80s across the state. And this trend is largely consistent with what we're seeing across the globe and consistent with the fact that our concentration of greenhouse gases in the atmosphere is changing. So we've seen that since 2012, 7 of our top 10 warmest years have occurred, and last year was the 4th warmest calendar year on record. So just a quick summary before we move on. The climate of our state depends strongly on topography, with elevation being the most influential factor. As we saw from some of these plots, the normals when we're talking about climate, they're almost philosophical because the weather varies so much from year to year that there's really no such thing as a normal year, or at least I haven't seen it yet. And our records do show that Colorado is warming over time, with some of the worst droughts on record being in recent years. And so now I'm going to spend a couple slides before we move into the shorter term outlook, talking about what's going on with this warming. And I mentioned the greenhouse effect. So the atmosphere is chock full of these things called greenhouse gases, with some of the main ones being carbon dioxide and water vapor. And a certain level of these are naturally occurring. And basically what's happening is we get all our energy from the sun, but then for the Earth to stay, why doesn't the Earth keep getting hotter and hotter and hotter when it's constantly being heated by the sun? It's because it's ventilating heat out to space, or emitting infrared radiation, as we call it, out to space in all directions all the time. And so that what keeps the Earth's temperature where it is the balance between the energy leaving through the top of the atmosphere and the energy coming in from the sun. And the energy that makes it out to the top of the atmosphere depends on how many greenhouse gases we have or how much insulation we have. And so when we have more greenhouse gases, it's like putting on a thicker and thicker blanket. And the greenhouse effect, to an extent, is a very good thing, because without any greenhouse gases, the Earth's equilibrium temperature would be about 0 Fahrenheit, and it would not be a fun place to live. Also, our best piece of evidence for the greenhouse effect is probably that we can survive the night. So if we think about Mars, Mars has a similar day length to Earth, where it takes about 24.6 hours to do one complete rotation about its axis. And the temperature varies by over 200 Fahrenheit between night and day. So you might get up to 100 degrees on the surface of Mars, but then you'll be below minus 100 during the nighttime. So again, not very comfortable conditions. But we do see that our concentrations of greenhouse gases are changing, and you can't have too much of a good thing. This is a plot showing our observed CO2 concentrations in the atmosphere going back to the 1950s from the Mauna Loa Observatory in Hawaii. CO2 is a well-mixed gas, so this is going to be representative of what you'd see basically anywhere around the globe away from a direct emission source. But you can see the red line is the actual observations, and the black line is kind of the annual average. And you'll notice that there's these wiggles from year to year, and that's driven by the fact that the northern hemisphere has much more land than the southern hemisphere. So during the summer in the northern hemisphere, or what we call boreal summer, June, July, August, when all that vegetation is growing, it's actually drawing down CO2 out of the atmosphere as part of its respiration process. But then it goes right back into the atmosphere when things become dormant in the fall. And this cycle is actually huge, but over time, it's actually small compared to the overall trend in greenhouse gas concentration. And we do see that our global temperature records follow a similar pattern. You'll notice that it's not exactly the same, where it's not, going up exactly in lockstep with our increase in CO2 concentration, because there is natural variability. And one of those big natural drivers in terms of global temperature, as well as what we experience regionally, is El Nino, or the El Nino Southern Oscillation. You'll notice that 1997 was an historically warm year at the time. That was referred to as a super El Nino, or strong El Nino, basically meaning that the sea surface in the Eastern Pacific was much warmer than it is in a normal year. And when you have warmer oceans, some of that heat gets vented into the atmosphere. Then you'll notice throughout the next 17 years or so, there was no significant warming, but that's in part because conditions reverted back to more La Nina-like conditions, where you have cooler waters over the eastern equatorial Pacific, and so it doesn't warm the Earth as much. But then, when you have this trend in greenhouse gases overlaid with this trend, with what's going on in the oceans, you see when we hit another big El Nino like 2015 and 2016, we warmed again, and now we've reverted to more La Nina conditions where it's kind of leveled out for the time being, but we expect it to continue to go up. And then here's how things have warmed across the US spatially. You've probably heard people talk about the 2C threshold, or 2 Celsius, trying to keep warming below 2 Celsius. As it turns out, there are parts of Western Colorado that have already warmed by that much. And I suspect that a lot of this is just happenstance, where we had an abnormally cool period at the start of this time series and an abnormally warm period at the end, with variability adding to what trend is there. But then this also could have to do with what's called land atmosphere feedbacks, where if you have dry conditions during summer, in a normal summer, some of the sun's energy is going to go into evaporating water, or into plants transpiring water out through their root systems. But when you don't have any water in the soils to give, you end up with all of the sun's energy going into just directly heating the surface. So that's, and we're going to talk more about that feedback here in a few slides. But how does this warming look in practice? Well, we know the weather can blow in any number of conditions, and so we see a range of possible temperatures. This is two kind of distributions of temperatures in July at that Grand Lake station in Colorado. The blue distribution being from 1940 through 1999, and the reddish pinkish distribution being in more recent years. And you can see they do have a lot of overlap, but we saw a lot more high temperatures in the 60s and lower 70s previously, whereas we see a lot more high temperatures in the mid to high 80s now. And we see this kind of migration of overall temperature distributions across lots of the state of Colorado. So where is this expected to go? Well, I'll have to step through this slide kind of slowly, but this is a look at what our temperature observations have shown across the state, as well as where things are projected to go in the future under a couple different climate model scenarios. Your y-axis here shows temperature change from the 20th century average, with the areas above zero being a warming and the areas below zero being a cooling. And then the x-axis, sorry that the zeros got cut off here, is just time. And so the gray bars show our observed temperature record. And then the stippled red lines and blue lines show output from individual climate models, with the red lines all being output from climate models where carbon emissions are not curtailed, and the blue lines all being from a scenario where carbon emissions are curtailed slowly over time. The solid blue line is the average of those climate model scenarios where emissions are curtailed slowly over time. The red line is kind of where they're not curtailed over time. And as you can see, there is a fair bit of uncertainty, but especially if we were to extend this out to 2100, there becomes almost no overlap at all. So while there is uncertainty, the biggest uncertainty factor is probably what humans choose to do. And then this is a sort of breakdown spatially and seasonally across Colorado for what's expected by the middle of the century compared to the average of the end of the 20th century. And we can see that warming is expected in all regions and all seasons, but less in the late winter, early spring, and more in the late summer, early fall. And that has a lot to do with that land atmosphere feedback that I was describing, where by the end of summer, if you're warmer already, you expect that the trees and grasses that you have are going to have to transpire more quickly. And so you lose your soil moisture more quickly. And by the end of the summer season, with these drier soils and less water for transpiration, you have more of the sun's energy going directly into heating the surface. This is how things are expected to change with precipitation, both regionally and seasonally. And we actually do expect in most regions that things could get a little bit wetter in Colorado in the cold season into mid-spring, largely due to the fact that warmer air can hold more water vapor. But then you see kind of a mixed signal, in part due to that land atmosphere feedback once we get into late summer and early fall. This image is just showing the same thing with more recent data for the Western US as a whole. And the only reason I included it is because the last slide is a little bit old, and this is showing some more recent Intergovernmental Panel on Climate Change data. All right, so one thing that I like to stress here is climate change is water change. So even if we don't have a trend in precipitation, and even if we do continue to have some years that are wetter than average, with higher temperatures, you get faster evaporation and evapotranspiration rates, which puts more stress on plants requiring more regular irrigation, which can reduce reservoir levels. And it can also make the droughts worse. So in a warmer climate, the dry years, in a sense, hurt more. And it can also change the timing of spring snowmelt. So you have a warmer snow season to deal with. And this slide is just to help drive home that point. Here we're showing output from a number of different climate models with precipitation change on the y-axis and temperature change on the x-axis. But the brown dots are showing model simulations where runoff actually decreases, and blue simulations are showing where it increases. And you can see kind of following this stippled line that you need a commensurate bump in precipitation in order to keep up with the temperature change, because without a bump in precipitation, if you just warm the surface, more of the water goes into evaporation and transpiration and less runs off into like streams and reservoirs. Okay, so a quick summary of this section, and then we'll move into what's maybe expected in the coming months. Colorado has been warming statewide with the strongest trends since the 1980s. Human emissions of heat-trapping gases are largely responsible for this. Long-term warming is expected to continue with high confidence. However, we will see strong natural variations from year to year. And then no long-term trends are really detected in precipitation, although the last 20 years on the average have been rough. And then warming will reduce to some extent our spring and summer stream flows unless precipitation also increases, which is possible, but we certainly aren't observing it at this point. We're hoping that that turns around. And then what happens with other types of extreme weather remains somewhat uncertain, but warmer weather does lead to, say, more fire weather conditions, which is something we can get into more with the shorter term outlook. And then in terms of expected changes, by 2050, the climate of Colorado will still be recognizable as the climate of Colorado, with plenty of snow in the mountains in most winters. Summers will, have warm days with relatively cool nights, keeping things pleasant a lot of the time. And precipitation will be highly variable from year to year, and we'll have regular problems with droughts, floods, fires, water availability, just like now. But some things that might change: snowpack is likely to melt a little earlier in the spring, more frequent occurrences of warm spells or heat waves, and less frequent cold snaps or extreme cold. When droughts happen, they'll likely be worse, increasing threats to water supply. And then destructive fires become more probable in warmer conditions as well. And there are compounding factors there too, like how many structures are in that wildland urban interface, things like that. So what's coming around the corner? Well, there are no corners, but let's talk about the seasonal outlook for a couple slides. And when we get into the seasonal outlook, it's important just to keep in mind where we're at currently. Snowpack statewide right now is pretty close to average, with Some areas like the Gunnison Basin even being slightly over 100% of average for this time of year, but other areas like the Yampa and White Basin being well below average. The graphic on the right-hand side is showing how that snowpack has built throughout the winter. The green line shows how it built in an average year, and then the red line is our historic low, the blue line is our historic high, and each shaded area kind of represents a percentile range, with the green shaded area being sort of our normal range. And you can see we got off to a really slow start this snow season, but around the holidays, we had a big boom in snow, and that's been very necessary, as then things dried out again quite rapidly. And recently we've been building more at average rates. Our warm spell over last weekend did knock things down a little bit. Let's see here. This is a map. Sorry, I skipped a slide there. This is the map of the current US drought monitor across Colorado. And you can see, largely due to long-term or multi-year drought, we're still showing drought across lots of the state, with short and long-term drought persisting right now in southeastern Colorado, but mainly long-term drought over the headwaters, with the winter conditions being decent this year. As far as where things are going, I'll start with the next 7 days and kind of move out from there. It does look like the tail end of this weekend into next week, you should get another nice dose of snow in the headwaters. So this map is showing whether precipitation is expected to be above or below normal over the next 7 days. And it's expected to be above normal throughout much of the headwaters area, which is nice, although that moisture won't necessarily be shared throughout the low elevations or the San Juans so much, with the San Juans being lower than average. So even though snowpack went down a little bit with the recent warm spell, it may come back up a bit and peak again or at its time in mid-April. Here's an outlook for the next 8 to 14 days. So kind of that second week of April. It looks like things are fairly uncertain in terms of what weather pattern will blow in. It actually looked like around the second week of the month, sort of later in the week, we could see a cooler weather pattern come back that may be conducive to snow in the Western Rockies, but will likely keep us dry out on the Eastern Plains and in Southwest Colorado. And then longer term, when we look at, say, a seasonal outlook, we have to think about, again, what's going on with El Nino. So the temperature patterns over the Pacific Ocean help dictate the structure of the jet stream over the mid-latitudes in areas like North America, where in an El Nino type setting, we're more likely to get those slow moving low pressure systems that track across the Four Corners area, New Mexico and the Oklahoma Panhandle. You may have heard of Four Corner cutoff lows or panhandle hooks. They're all the same kind of system, but they move slowly enough to allow time for large swaths of moisture to well up from the Gulf of Mexico or Eastern Pacific and really give us good precipitation across much of the state. Whereas under La Nina conditions, those tend to occur less frequently, and we get more of the storms that kind of clip the northern half of the state. And those can be okay for the headwaters, but we tend to do better during El Nino years. And right now, La Nina is actually hanging on longer than was expected, and it's likely to hang on into the summer and perhaps the fall. And typically, this is kind of the pattern that we expect to see across the contiguous US under La Nina conditions. And this drier than normal area really does extend up into much of Colorado, especially in the spring and summer. And this plot is just designed to show that. So this is a correlation analysis showing whether El Ninos or La Ninas are wetter in Colorado using data from 1981 through 2020. And it's broken down by season. So you have December, January, February in the upper left, March, April, May, upper right, summer, lower left, fall, lower right. Areas that are red are wetter in El Nino. Areas that are blue are wetter during La Nina. So La Nina can actually be sort of a good thing for the Northern Rockies in winter, but once we get into spring, El Nino tends to be better everywhere. And seasonal forecasts are typically fairly uncertain, so there's definitely a chance of wet weather in spring and summer during La Nina. It's just like, it's kind of like playing poker with a deck of cards that's missing a couple aces and a king. You know, you still could have a great hand, but the odds go down. And so that's what we're looking at for the late spring and summer, is that combined with our trend towards these warmer summers, we're more likely than not to have a warmer than normal summer and could have a drier than normal spring as well. So using that kind of information, as well as input from seasonal forecasting models, this is the outlook for April released by the the Climate Prediction Center. And we see an increased probability of above normal temperatures and below normal precipitation throughout the state this April. Like I said, it looked like cooler weather could return in the middle of April. So I might, based on what we're seeing in the more short-term weather models, I actually might knock down these probabilities of above normal temperatures a bit, and maybe even the precip too, although we'll see. And then if we look at the season as a whole, we see that there's an increased probability again of above normal temperatures and below normal precipitation throughout April, May, June is what these maps are showing. And then the next map just takes it into May, June, July, and we see these conditions likely to persist. So the deck is sort of stacked against us in terms of short-term relief. And that's likely to make a difference this summer in a couple ways. For one, even though our snowpack is currently fairly close to normal, because conditions were dry and soils were dry going into this cold season, and because our forecasts are leaning towards the drier side, stream flows from April to August of this year are likely to be a little bit on the lower side of normal. So we have 91% of normal for the headwaters, which isn't too bad. And again, like 95 for the Gunnison, which especially isn't too bad. But then some of these other basins like the San Juan, Upper Rio Grande, Arkansas, particularly the southern half of the state that does worse during La Nina conditions, we're likely to see below normal runoff this year. And then in terms of the fire outlook, here's the outlook for significant wildfire potential by June of 2022. And because we're looking at an elevated probability of an early snowmelt, June 2022, we actually do see an elevated fire weather threat or fire conditions threat across much of western and southern Colorado for June 2022. So certainly this is going to be a good year to use water wisely and follow any burn bans that are in place, because we just hate to see those large wildfires occur. I can talk more about Kokoras in a minute, but I do want to stop there and pause for questions, comments, and then maybe I can elaborate a little bit on my last couple slides.
Thanks, Peter. I think, Taria, you had a question you put in the chat room about, she asked, will Colorado increase the practice of cloud seeding in hopes of increasing precipitation to balance out the warming temps? What do you think?
Yeah, that's a really good question. And not that I know of. Cloud seeding is interesting because the data on it aren't particularly conclusive as to whether it actually increases precipitation or not. You know, a lot of the cloud seeding studies, it'll show like increases precipitation by 5% plus or minus 15%. So it's just kind of a hard thing to work with. It's also, if it does work, it can be kind of a robbing Peter to pay Paul thing, because the atmosphere only has so much water vapor. So if you coax it out in one area, it's going to be drier downstream. So it's something to think about in terms of doing it responsibly. But yeah, in terms of increased cloud seeding, not that I'm aware of.
Yeah, that's interesting. And yeah, I mean, I learned a lot about, I didn't really think about it that way. So thanks for your good question. Marty Todd had asked, have they changed the years used for averages?
Yeah, that's a really good question too. So typically when I was showing slides that give a percent of average, like 90% of average with the stream flow or the snowpack or something like that, that is with reference to 1991 through 2020, whereas it used to be we'd use our frame of reference as 1981 to 2010. And so there are some differences there. Certainly the new averages are warmer. So when I'm comparing things to the 1991 through 2020 averages and say with the seasonal forecast, there's an increased chance of above normal temperature, that would be even more increased with reference to 1981 through 2020, or sorry, 2010, or even more so with reference to 71 through 2000. So we always use the most recent full 3 complete decades, just because that gives us a good sample of what kind of recent variability that we've seen. But we do need to be cognizant of how things are changing over the long term. We're certainly seeing that is important. One thing that I would say about the new normal period is when it comes to things like precipitation and snowpack, the normals haven't changed as much as you might think. And part of that is because there's a lot of overlap there. Both periods include the 1990s and the 2000s. So that sort of mutes the influence of trends.
Oh, interesting. I also, Michael Morin had a question. Are there any specific conditions that can predict the atmospheric conditions for the upcoming year, or conditions that can predict whether it will be a drier precipitation year?
For the upcoming year, are you talking about, say, the next snowpack cycle, or are you talking about this summer?
Michael?
Would be my question.
I don't know if he has, let's see if he's actually responded to that. Snow.
Okay, snow. Yeah, I mean, we would look forward at the kind of outlook for El Nino, La Nina in the coming year, as well as thinking about trends. But then we would also look at things that are a little bit more stable, like the Pacific Decadal Oscillation, which is a similar to El Nino, is a sea surface temperature kind of pattern oscillation, more in the northern Pacific than in the equatorial Pacific, but it changes more slowly, like on a 10-year time scale. And depending on what phase that's in, we actually do see an influence in precipitation over some of the western US, including Colorado. And the signal is pretty weak, so there's not a whole lot to go off of. You can certainly have a wet or dry year when the Pacific Decadal Oscillation is positive or negative. But it's again, I like to use the deck stacking analogy, where when it's in the negative phase, like it is right now, with cooler waters off of, say, the coast of California and warmer waters over the central Pacific, we tend to see a little bit less precipitation on average, or a little bit drier winters. Whereas when it's in the warm phase and you have warmer waters off the Pacific coast in the western US and cooler waters more over the central Pacific, we tend to see a little bit wetter winters. So again, there's a lot of variability, and these seasonal predictions leave a lot to be desired in terms of skill. I don't want to be shy about that, but things are sort of weighted in favor of a little bit lower snow and keeping the long-term drought in place.
Oh, interesting. These are all good questions. So Toria had a question about what are the top 3 things we can do as individuals to change the course of warming temps? It's a big one.
Yeah, that's a really awesome question. And I will say that much of the developed world is already, kind of on the right track, where for the US, annual carbon emissions peaked in like 2007, 2008, and they actually crashed a little bit with the economic downturn after that. And even when the economy came back, emissions didn't necessarily come back as the price of renewables got more competitive. So we are seeing that in places like Europe and the US, carbon emissions are going down slowly. But in places like the developed world, they're ramping up, and it's kind of hard to blame them for that when we've been reaping the benefits of kind of a high emission lifestyle for so long. So in terms of the global picture, I would say, advocating for, policies that reduce our emissions and help the developing world develop more cleanly. In terms of individual actions, driving and flying less, consuming less red meat, and heating your home efficiently are some of the best examples. But it's quite the quagmire, right? Because it goes well beyond the individual level, and so it just takes so it's a very multifaceted problem, and it takes solutions at multiple levels.
Yeah, absolutely. Yeah,
Yeah.
it's a big one. But if we all do a little bit,
Sure, it does make a difference.
Absolutely. And Marty Todd had a question: is anyone talking about diverting water from the east and west, like piping from the eastern states? The pipes are in place under the Continental Divide, just reverse flow. Yeah.
Oh, interesting. So is anyone talking about piping from east to west? I don't think anyone's talking about that with the Denver metro area growing the way it is. I worry that if anything, there's more talks about sending more water west to east. So that's, but I think that the bigger problem there is, what's going on with Lake Powell and Lake Mead long-term, and that Colorado River compact that was really set up based on our experience in wetter years. What sort of curtailments is that going to lead to down the pipeline? I don't know, but we're in a situation where, Colorado itself could recover from long-term drought in one really good year or two pretty good years. But if you look at the water supply situation in the greater Southwest US, it would take more than that. And I think it over the long term, we're going to have to rethink some things.
Yeah. Yeah. Hopefully with the Colorado Water Plan and some of the things that are discussions across the state, we can relook at some of our Colorado water law and some of the things that we've done.
Yeah.
Anyways, right? So does anybody else have any other questions at all for Peter? No, I don't think so, but thank you so much, Peter. You've done a fantastic job, and it's been extremely interesting. Just for everyone, we'll have this, this is recorded, and we'll put this on our website at Headwaters, riverjourney.com, and we'll have it in our water news section. And in there, where we'll have the rest of our virtual series talks. And just take a look at our calendar, and we will continue to do these virtual speaker series every month. And please, if you'd like to, I invite everyone to attend our Earth Day on April 22nd from 3 to 7 at the Headwaters Center. We're doing a huge celebration. We have like 10 organizations that are doing like interactive fun activities and having music, and we'll have a cash bar and all that. So please come. But thank you, Peter. Thank you, everybody, for attending. And I look forward to seeing everybody next time.
Yep. Thanks, everyone, for joining us. And thanks, Holly, for having me.
You bet. Absolutely. You guys take care. Thank you.